The basis of a vector space is summarized as the set of vectors from which all other vectors can be formed. After viewing this video and taking careful notes and perhaps working through some of the problems, your objectives will be to develop the ability to explain what base vectors are and how they relate to the other vectors in the vector space. That's your first objective. The second is you'll be able to explain what the dot product of two vectors reveals about the angle between the vectors. And finally, you'll be able to describe the properties of an orthonormal basis. So let's remind you again what a vector space is. And we'll refer to vector space as S. It's basically the n-dimensional space containing all possible vectors. If you've taken calculus and Calc 2, you've probably primarily worked with two-dimensional vector spaces or perhaps three-dimensional vector spaces. But as vectors can, have n elements in them, in general, there can be an n-dimensional vector space. So now let's talk about definition of a basis. And you can also see page 449 for some formal theorems about bases. So the basis of a vector space is the set of linearly independent vectors and we'll refer to those vectors as little e's for base vectors, and there could be in general n of them, from which each and every other vector can be formed by linear combination. That is, that if we have an arbitrary vector x, it is formed uniquely by the linear combination of the given base vectors. So that's a formal definition of the basis. So for example, in 2D space, or I should say 2D space has, or I guess is defined by the span of two base vectors, E1 and E2, with that set being the base vectors, or that set being the basis. And for example, is the plane of this computer screen. So we could define that basis, for example, we could sketch them as, say, E2 going in that direction and E1 in another direction. They have to be in different directions in order for it to have a span being in a plane. And so we can illustrate that vector x, for example, can be formed by say E1 times 1 plus, well, let's see, E2 times 2. I didn't draw my x vector long enough. But that would be an example of a vector that is formed by a linear combination of these base vectors, and any vector in the plane of this computer screen can be formed by a similar linear combination. Now, an orthonormal basis is a special kind of basis, and it is made of unit vectors in other words, their magnitude is 1. Their magnitude or length is equal to 1. And each is orthogonal to all the other vectors. So there's a definition here that I'll talk about orthogonal. And the unit vectors are typically defined with hats or carets on top of them instead of bars. So the little carets or hats denote unit vectors. And so we would write an orthonormal basis, for example, with e's with carets. So let's now talk about what is orthogonal. And to do that, let's remind ourselves what the dot product of two vectors is. The dot product is also sometimes called the scalar product. So if we define our vectors as n by 1, n rows and 1 column, for example, and we define 2 of them, then the dot product of x and y is equal to the matrix product of x transpose y. And so we can write that out in indicial notation with the indice I, and it's being summed from 1 to n, and that's the product of each element x sub I times each element denoted as y sub I. So that's mathematically how we carry out a dot product. Now, you've seen the dot product in your calculus classes as described in 2 or 3D space. as, for example, x dotted with y being equal to the magnitude of x times the magnitude of y, and I'm using the double bars to denote magnitude, or the length of the vector. And that's the product of the magnitudes times the cosine of theta, where theta is the angle between the two vectors. So if x dotted with y is equal to 0, then theta is equal to 90 degrees, and the vectors are said to be orthogonal. I should state that this defines what orthogonality is, the dot product of two vectors being equal to 0. And in 2 and 3D space, you can interpret that as the angle between them being 90 degrees. But this property holds for, for any n-dimensional space. So we're defining an orthonormal basis here, and we've talked about the orthonormal basis being made of unit vectors, and also they're also orthogonal, and we've defined orthogonal as being such that the dot product of any of the vectors is equal to 0. So another aspect about the orthonormal basis another way of stating that each of the vectors are orthogonal is that we could say that if we dotted the ith base vector with the jth base vector, then that will equal the Kronecker delta. Where when I is equal to j, then the vectors are the same, and the dot product of two unit vectors that are parallel to each other is equal to 1. And again, if I is not equal to j, then the two vectors are orthogonal, and so the dot product is 0. And a commonly used orthonormal basis in 2D or 3D space is the Cartesian coordinate system. I should say the Cartesian coordinate system is defined by this orthonormal basis. So a commonly used orthonormal basis in 2 or 3D space defines the Cartesian coordinate system. And you've learned about the Cartesian coordinate system, and now you're learning that it is formed by an orthonormal basis. So you may have learned how to define vectors in terms of the unit vectors parallel to the x-axis, the y-axis, and z-axis, and that's an orthonormal basis. And we could equally describe those same unit vectors as E1 hat, E2 hat, and E3 hat. So that's a summary of the basis of a vector space, and this concludes this video.